Hello everyone, welcome to my YouTube channel. So today I'm going to explain to you how you should answer all the questions from quiz 1. Altogether we have 6 different questions and let's start with the first one. In the morning, a paintball pressure tank is at 306 atm. The weather heats up over the course of the day and by 3 p.m. the outside temperature is roasting at 38.5 degrees Celsius with pressure inside the tank raised up to 324 atm. What was the pressure in the morning? So how are you going to tackle this question? So what we should do is we need to use the formula P1 over T1 is equivalent to P2 over T2. So let's look at the initial pressure. So the initial pressure is 306 atm. So P1 is 306 and the initial temperature is the thing that you need to calculate. And then moving on, the final pressure it raised up to 324 atm and the final temperature is 38.5 degrees Celsius. So you need to change it to Kelvin to 73. Right, so from here you shall get 306 over T1 is equivalent to 324 over 311.5. So therefore, you can calculate T1 is 306 times 311.5 is equivalent to 324 T1. Therefore, your T1 is equivalent to 294.1944 Kelvin. But if you can see in the objective question, the answer that you should be giving is in degrees Celsius. So what you can do is 294.1944 Kelvin. You need to minus back with 273, so you shall get 21.1944 degrees Celsius. So this is the final answer for this question. Let's move on to the second question. A 40-liter balloon is filled with air at sea level where the pressure and the temperature is 1 atm and 25 degrees Celsius respectively. It is tied to a rock and thrown in a cold body of water and it sinks to the point where the temperature and the pressure are 4 degrees Celsius and 11 atm respectively. Determine the new volume of the balloon. So from this question, it is clear that you need to use the combined gas law whereby the formula is P1 V1 over T1 is equivalent to P2 V2 over T2. Right, so from here we can see that the initial pressure is 1 atm and the initial volume is 40 liter and the initial temperature is 25 degrees Celsius, but you need to convert it to Kelvin to 73. Right, moving on to the final pressure. So the final pressure is 11 atm. The volume is the one that you want to calculate, V2, and the temperature is 4 degrees Celsius. So you need to convert to Kelvin to 73. So after you have calculated this one, you shall get 40 divided by 298 should be equivalent to 11 V2 divided by 277. So from here we can calculate your V2 is actually equivalent to 11 0.080 divided by 3278. So you shall get your volume is equivalent to 3.3801 liter. So this is the final answer for the second question. Let's move on to question number 3. The pressure of gas is reduced from 1200 mmHg to 113324 Pascal as the volume of its container increased by the movement of the piston from 85 ml to 350 ml. Determine the final temperature in Kelvin if the initial temperature is 90 degrees Celsius. So from this question, the first thing that you should notice is that the unit that they use for the pressure is different. So all you need to do is you need to convert all this pressure to the constant unit, which is the ATM. So the first one I'm going to convert is the 1200 mmHg. Converted to ATM, it should be equivalent to 1.5794 ATM, whereby 113324 Pascal should be equivalent to 1.1187 ATM. So how are you going to convert this? I'm not going to explain in this video, so you should know how to convert it. First, you may convert it automatically from your calculator, but it's better for you to know how to convert it manually. Alright, since you already have converted this unit, so the next thing that you need to do is you need to look back at the question and think of what formula that you can use. Since you were given the pressure, volume and also the temperature, so obviously you are going to use the combined gas law. So in the combined gas law, again, it is P1V1 over T1 is equivalent to P2V2 over T2, right? So the pressure is equivalent to 1.5794, and the volume, the initial volume, is 85 milliliter. So you need to convert this milliliter to liter, so you need to divide it with 1000. So divided by the initial temperature is 90 degrees Celsius, so 90 plus 273. Alright, so you need to look at the final pressure. So the final pressure is equivalent to 1.1187 times the volume. The volume is 350. So divided by 1000, because you want to convert it to liter, and then the final temperature is the thing that you need to calculate. So from here you should be able to calculate this, and you shall get your final temperature should be equivalent to 1058.5944 Kelvin. So this is the final answer for the third question for your quiz 1. Moving on to question number 4. A gas in a system has constant pressure. The surrounding around the system lose 62 joule of heat and does 474 joule of work on the system. What is the internal energy of the system? So in this case, you will ask to calculate the internal energy for the system. So the internal energy for the system, the formula is delta U is equivalent to Q minus W, right? So now what you need to do is you need to determine whether your Q and W should be positive or negative. So let's see the first one. A gas in a system has constant pressure, okay? and then it says that the surrounding around the system lose 62 joule. So once the surrounding lose energy, it means that the energy is being absorbed by the system from the environment. So we can say that when the system is absorbing the heat, it means that the heat is positive. So Q must be positive, right? And then it states here that the surrounding does 474 joule of work. So the work is being done by the surrounding, not by the system. Therefore, your W should be negative. Right. So you need to get this one straight first. Once you get it, then only you can plug in the value inside your formula. So your Q must be positive. So your Q should be 62. But your W should be negative because not the system is doing the work, but instead the surrounding is doing the work. So now you should do negative 474. So from there, you will get 62 plus 474. So you should get 536 joule. Right, this is the final answer for the fourth question. Moving on to question number 5. A cylinder contains 7.0 gram of nitrogen gas. How much work must be done to compress the gas at constant temperature of 80 degrees Celsius until the volume is half, given that the atomic weight for nitrogen is 14.0067 gram? So from this question, you should know that it states here that it is at constant temperature. So we can assume that this process is following the isothermal process. So you were asked to calculate how much work. According to the theory, in the isothermal process, the work is equivalent to nRT ln V2 over V1. So in this question, you were not given the number of mole, but instead you were given the mass. So from this mass, you can actually calculate the number of moles. So number of mole for nitrogen gas is equivalent to mass over RMM. So given to you the mass is actually 7 gram and the RMM is because you have N2, right? Because it's in the gas. So 2 times 14.0067. So you should get the number of mole for nitrogen gas equivalent to 0.2499 mole. So now since you already have the number of mole, so we can calculate the W. So W is equivalent to the number of mole 0.2499 times R, which is the constant value 8.3145 ln T, your T is 80 degrees Celsius, so 80 plus 273, so ln V2 over V1, right? So we shall calculate this part first. So W is equivalent to 7.3346 times 10 to the power of 2 ln V2. Your V2 is half of whatever in the V1. So we assume that V1 is equivalent to 1, so half of them shall be 0.5. So 0.5 divided by 1 is 0.5. So you should get your W is equivalent to 5.0839 times 10 to the power of 2. And then the next thing that you need to do is you need to look back at the question. So how much work must be done to compress the gas at the constant temperature of 80 degrees Celsius. So work done to the system, right? So the cylinder is the system. So how much work to be done to the system? So your unit for W should be negative. So instead of positive here, your final answer should be W is equivalent to negative 5.0839 times 10 to the power of 2 joule, or you can also write it as negative 508.3965 joule. So this is the final answer for the fifth question. Right, now we are at question number 6. The air in an inflated hot air balloon absorbs 125 joule of heat from its proximity to a fire. The balloon expands and does 8.5 kilojoule of work. What is the change in the internal energy for the system? So we are going to use the same drill because you were asked to calculate what is the change in internal energy. So change in internal energy is delta U is equivalent to Q minus W. So the rule of thumb in using this formula is that you need to know your Q and your W should be in positive or negative sign. So the first thing that you need to see is that the first one is the heat. The hot air balloon absorbs 125 joule of heat. So your system is actually the hot air balloon and the surrounding is the fire. So the system absorbs heat. Since the system absorbs heat, so your Q must be positive. And then moving on, it says that the balloon expands and does the work. So the balloon is actually the system. So the system does the work. So system does the work, your W must be positive as well. So delta U is equivalent to Q. So since your Q is positive, so you just have to write 125 minus W. Your W should be positive as well. 8.5 kilojoule, right? But you need to always be careful, and you see this one is in joule and the other one is in kilojoule. So you need to convert this kilojoule into joule, so you need to times 1000. Therefore, what we shall get is equivalent to 125 minus 8500. So we can say that what we will get is negative 8.3750 times 10 to the power of 3 joule. So from here we can convert back into kilojoule. So you shall get negative 8.3750 kilojoule. So this is the final answer for the last question for quiz 1. Thank you very much for watching this video. I hope this video will help you understand more of what we have learned last week. So I'll see you again in the next video and our lecture. Take care and stay safe.